Hello, and welcome to a couple of examples of using impulse change in momentum. So here's example one. May look familiar from last year. A 250 Newton force is applied to a 30 kilogram object moving at 25 meters per second to bring it to rest. A. How long is the force applied? Now, we might be able to do this problem a different way with kinematics and a force analysis and things, but since we're doing impulse and change in momentum, let's apply that idea. Right, we know that if this is a constant force, the force times the time, which is impulse, is equal to the change in the momentum. Change in momentum is, of course, final momentum minus initial momentum. And the final momentum here is 0 because we're bringing it to rest. So that means the impulse is equal to negative mass times initial velocity. Remember, of course, that momentum is mass times velocity. Mass in motion, if you will. Solving for the time, which is what we're looking for, right? We can do this all in one equation without needing any kinematics or anything like that. Right? And so the time is equal to the negative of the mass times the initial velocity over the force. So we plug our numbers in, and we have to be a little careful here. This force is taking an object which is moving and bringing it to rest. Therefore, the force must be applied in a direction opposite the motion, and therefore it's negative. If you miss that negative, you'll end up with a negative time, which won't make any sense, right? So hopefully you see here that this needs to be a negative force to imply that it's acting against the motion and bringing the object to rest. Plugging those numbers in and working out the units, you get a nice round 3.0 seconds. So that's how long it would take the 250 Newton force applied to a 30 kilogram object moving at 25 meters per second to bring it to rest. And again here, notice we didn't have to do F equals ma, we didn't have to do a kinematic equation, which we actually don't have enough information for. We only know the initial and the final velocity. Right? And so we would have a hard time doing it that way, but impulse change in momentum gets us there. Part B, what if the time lasted 6 seconds, twice as much time? Well, you might be able to think this through proportionally, but let's work it through again. Impulse is equal to change in momentum. Final momentum is 0. Force times delta t is equal to negative m times the initial velocity. This time we are solving for the force. Plug in our numbers, and notice we get a negative answer, which kind of jives with our previous one. And we get a not so surprising negative 125 newtons. Notice that that's half the force. Well, how could it be half the force? Because it was twice the time to do the same change in momentum. You might remember doing a bunch of problems like this, and there will be a bunch more when you're doing MOPs and things, if you review the MOPs, where they ask you to proportionally think. So I probably wouldn't have even have written out all of this math, as much as I like writing out the math. Right? I just would have looked at this proportionally and said, oh, okay, all things being equal, twice the time means half the force to get the same impulse. Twice the time requires half the force. This is the whole point of airbags, seat belts, all those kinds of things. Right? Anti-lock brakes. They increase the amount of time it takes to stop and decrease the force of impact. Right? And that way, you don't get hurt as much. Big force, little change in time, is the same as a big change in time, little force, if we want to be very graphic about things. Here's one that we didn't do last year. You have a 0.45 kilogram baseball thrown horizontally at about 40 meters per second, about 88 miles an hour, hit by a bat such that the ball leaves the bat, traveling at 45 meters per second at 45 degrees. So the ball comes in, we're assuming horizontal to keep things nice, hits the bat, comes off right at a 45 degree angle, which of course would be the ideal to make it go the furthest. So I want to know what impulse was given to the ball by the bat. The impulse given to the ball by the bat. Okay? Now, we don't have enough to just calculate the impulse with force times time. So if we tried to do that, we don't have the information. What we do have, however, is that impulse is equal to the change in momentum. But you'll notice that this is not a one-dimensional problem. This is a two-dimensional problem. And so as we've done in the past, in order to work a two-dimensional problem, we will split it up into two one-dimensional problems. And those dimensions will be perpendicular to one another. Perpendicular vectors are independent of one another. So we're going to say that the x component of the impulse has got to be equal to the x component of the change in momentum. And likewise, the y component of the impulse has got to be equal to the y component of the change in momentum. So again, we're taking this two-dimensional problem and breaking it down into two one-dimensional problems. And then afterwards, we will put them back together and make a one-dimensional answer. So let's start out with the x. Okay. The horizontal component of the impulse is equal to the final x momentum minus the initial x momentum. Momentum is mass times velocity, so the x component of the impulse is equal to mass times the final x velocity minus mass times the initial x velocity. Of course, we can factor out the m. And now we have to be a little careful. Okay? This is the final x velocity. So that's the final velocity. So this is the final x velocity, and this is the final y velocity. Right? We have to break it up into perpendicular components. So, hopefully you can see the trig here. The final x component is the final velocity cosine of 45 degrees. The initial momentum is all x, so we don't even have to put an x on it. And we could make these more complex, but it's a one-dimensional initial velocity, right, which is all x. So we plug in the numbers, and notice we have to be careful of one thing here. The x velocity is to the left. So if we want to keep consistent with our directions, a conventional coordinate system, we need to make this a negative 40 meters per second. And plugging in all the numbers, we get an x component of the impulse of positive 32.3 Newton seconds. Now again, this is the impulse given to the ball by the bat. So the bat's going to hit the ball, right, to the right and up. Right? So this is a positive x component. So that's the x part of the impulse. What's the y part of the impulse? Well, a similar process. Final y component of the momentum minus the initial y component of the momentum. The initial y component is 0 because it's all horizontal initially, right, coming in before it hits the bat. The final component of the momentum is mass times the final velocity, vertical, the vertical component of the final velocity, if you want to say it nicely. Plug in from our vector diagram over here that VFY is VF sine of 45 degrees. Plug in the numbers, we get a y component of 14.3 Newton seconds. So these are our two answers. We can write this in two ways. Here it is in unit vector notation. The impulse that the ball gives to the impulse given to the ball by the bat is 32 Newton seconds I cap plus 14 Newton seconds J cap. We also could write this in polar coordinates or magnitude and direction. If we draw out the vector diagram, there's 32 Newton seconds I cap, horizontal. There's 14 Newton seconds J cap, vertical. There is the impulse and the angle of the impulse. Quick little Pythagorean theorem gives us a magnitude of 35 Newton seconds. Inverse tangent gives us the angle, 24 degrees. And so the answer in polar coordinates, the impulse given to the ball by the bat is 35 Newton seconds at 24 degrees. And of course you should be able to do these both ways. Last part here, the opposite question. What impulse was given to the bat by the ball? And it is literally opposite. Because after all, the force that the bat puts on the ball would just be equal and opposite to the force the ball puts on the bat by Newton's third law. And the time of impacts have to be the same. Right? The bat hits the ball just as long as the ball hits the bat. And therefore, the impulses have to be equal and opposite. Right? Force times time, right, is impulse. So if we multiply both of these, the impulse of the bat on the ball is just equal in size and opposite to the impulse of the ball on the bat. So if we change the components, right, they were both positive, so we make them both negative. Draw out our new vector diagram, 32 Newton seconds to the left and 14 Newton seconds down, and there is our impulse. This happens to be 204 degrees because it's the opposite, right? It's the same inverse tangent. So this is the same angle as before, 24 degrees. But now to name it from 0, I have to go around to 240. And we get 35 Newton seconds at 204 degrees. Notice that's 180 degrees from the impulse on the ball by the bat. So hopefully you see here that we really don't have to do any calculations. We just have to understand that impulses are force times time. And by Newton's third law, the forces are going to be equal and opposite, the times are going to be equal, and therefore the impulses have to be equal and opposite, and boom, you're done. Hope you enjoyed these examples and hope these help you on the first packet.